Welcome to Fossils and Fiction, the podcast where we explore the culture and science of paleontology. I'm media researcher and dino geek Travis Holland.
And I'm paleontologist and weird bug enthusiast Alyssa Fjeld. Each episode, we uncover the incredible stories behind fossils and meet the people who study them, create art inspired by them, and bring prehistory to life.
It is a new era of Fossils and Fiction. Your regular host, Travis, that's me, is here. But I also have a brand new co host. You will know her from a previous episode, which is one of our most popular. Her name is Alyssa Fjeld. Hi, Alyssa.
Hello, Travis. It is me, Alyssa, your local weird bug enthusiast and paleontologist. I'm super stoked to be joining the show as a co host, and I'm looking forward to recording some great new episodes.
I am so happy to have you on board because you actually know what you're talking about. I mostly just ask random questions of paleontologists, and that's been the show for the last 3 years.
To be fair, we do like to be asked random questions. Surprisingly few people ask me what my favorite dinosaur is.
What is your favorite dinosaur?
A Parasaurolophus. It goes honk honk. That's all you need.
Have we never discussed this before? Because that is absolutely my favorite too.
No way! I don't
Yeah,
think we
it has
have.
been for such a long time. Brilliant start. See, I knew this is why we're friends. Alyssa, you went on a trip to the US recently to check out some museums. Tell us a bit about that trip.
Did. It was a really great time. I was primarily going for research purposes. So, one of my PhD chapters focuses on larger phylogenetic trends in trilobites. So, how the axial growth, the mid part of the bug, is growing across a wide diversity of animals. They're all from the Cambrian and they're all still bugs, but it was nonetheless a really exciting time getting to see some different species and visit behind the scenes. And in a couple of cases, I also was able to look at some other species. So in the Springer room, where they keep all of the trilobite fossils and the type specimens, they also have all of the amber and several of the different fossil fish species and fossil shark species. That was really exciting.
That was at the AM&H.
That one is the Smithsonian. Springer Room is in
See,
the Smithsonian.
see, this is what I mean. I don't know what I'm talking about, so I have to ask these details. But you went to the AMNH and you went to the Smithsonian. Did you go anywhere else?
I also visited the ROM just as a guest, but I think that was probably as much as anyone would want. I was very stimulated. I was very in my zone, explaining all of the little creatures to random passerbys and my beleaguered parents who joined me.
It sounded like such a great trip, and you put up some amazing photos. So, look, I am so pleased to have you here as a co host. Alyssa, each week we are going to focus on one big paleo story of the week. Other podcasts, some of our favorites out there, might do multiple news stories, but in each episode, we're just going to pick one that we like and chat about it. I've been referring to this one as the frozen murder kitty toe beans. Tell us about the mummified homotherium kitten.
I would love to. This is arguably somewhere between tragic and absolutely adorable. Sorry.
As most paleo is, let's be honest. I mean, we only get cool fossils because these things died, and usually, or quite often, not, at the end of a long life, often
Yes.
violently, or often because they were buried by an avalanche or a volcano or something. So it's tragic, still cute.
Very cool. And it's teaching us a lot about how the early growth of homotheriums or saber-toothed cats might have taken place. It's always sad when we find juveniles, but they tell us how animals may have grown through their life, which is really interesting and exciting for us as scientists. This particular little cub was found in Yakutia, Russia. I'm almost certainly saying that wrong, in the Bajarica River. It's an upper Pleistocene deposit and it was found in the permafrost. So this is an actual mummified little kitten. It still has the fur and of course the toe beans are still intact. In the paper, the specimen was described as having foot pad and claws that are preserved on the plantar surface of the front paw. The shape of the second, fourth digital pads is sub-squared in contrast to the oval digital pads of the lion and other felidae, that's cats. The metacarpal pad is bilobed and bean-shaped. How cute is that?
Even the scientists writing up this amazing find couldn't resist this. So I also understand that this is the first time we have found something this well preserved where we don't have a similar animal. So it's essentially mummified. It has fur, it has all of its internals in place. It frozen in the permafrost. I think only from the front half up, the sort of top half of the rib cage, and then the head and front paws. But yeah, a 3-week-old frozen kitten from Russia of the saber-toothed cats or the homotherium, which is just, it's an incredible find, and it can tell us so much about how these animals grew, as you said, and also their closer relatives and how they are similar and different to those other relatives. It can inform so much about how they're viewed, I think, in pop culture as well. So just absolutely an incredible find, and something we're not going to get with those older animals that you study or with dinosaurs, but for animals from the Pleistocene to see something like this, I think most people would dream about this.
Yeah, I mean, I think it's always a bit of a shock and a bit of excitement when you find something that is so intact, that is 32,000 years old. It's absolutely incredible. And to think this was the kitten that would have, in other circumstances, grown up to nosh on our ancestors' skull plates.
The first thing that you got to do, the first assignment for the pod, was to go out and have a chat with another paleontologist, someone who I think you know pretty well already. Introduce this chat for us.
Yes. So Steph Richter-Stretton and I did some field work together. It was a really exciting break from the pandemic lockdowns, being able to go out to the desert and dig up some very cool early Cambrian, what are called small shelly fossils. Steph was doing part of her honors degree during that time looking at something called the Red Horizon. Steph is a stratigrapher at heart, which is why you can find her on social media as biostratigraphy. And in amongst all of her stratigraphic assessments of different early Cambrian sites, so looking at the ways that the rocks sit on top of one another and comparing those to different international sites, which is a really cool thing that not a lot of paleontologists get to do in the early Cambrian, this multi-proxy approach that lets you compare different beds. It's a really rare thing to find because we don't have globally distributed species, and often we don't have volcanic ash or other components that can tell us more definitively where we are in time. So in addition to doing that, which is already super cool, Steph also looks at that group of animals I mentioned before, these small shelly fossils. These are really enigmatic, but I think quite charismatic fossils that were biomineralizing or producing hard surfaces early in the Cambrian. So she's a little bit of a wizard to me. She looks at all of these amazing but very strange things and manages to tell a cohesive story.
Let's get to the interview with Steph.
I'm recording my very first episode today with my special guest, a paleontologist and geologist that I'm very familiar with from my time at Macquarie University and as just part of the general Cambrian crew around Australia. Please welcome Steph Richter-Stretton, pronouns she, they. Steph, how are you today?
Hi, I'm great, thanks. Alyssa, how are you?
I'm doing well. It's a sunny, beautiful day here in Melbourne for a rare change of pace. How about Armidale? How's that going?
We are completely the opposite here today in Armidale on at the Mutna country. It is very rainy and cold and all the sad things. So I'm very glad to be inside nice and warm and having a chat to you.
So, Steph, you're up in New South Wales at a rural university called the University of New England in Armidale. Can you tell us a little bit about what that uni's like?
I've done all of my tertiary education through from my undergraduate bachelor's degree through to my honours thesis, and now I'm a PhD candidate through the University of New England, or UNE. And UNE is really awesome in the fact that it offers distance education. So I did most of my undergraduate bachelor's through distance education. I'm from regional Queensland, and it was really awesome to be able to work from home and not have to leave. I didn't really have the financial ability to leave home right away. And now on campus, it's really wonderful. We have such a lovely, tight-knit community. Unfortunately, sometimes I guess a downside of being such a online provider is we don't have as many students on campus. But what that really results in is these really wonderful, tight-knit communities between the students and also the lecturers and other academics. And I think that just makes it so worthwhile.
I would agree. I think that there's a really nice environment at UNE from the visits that I've paid there. So, in full disclosure, two of my advisors, John Patterson and James Holmes, are both at UNE. So, I'm a little bit biased, but you guys are now, or at least I should say, Marissa and Nick Campione, who are both at UNE, are now they're playing some role in the Australia Asian Paleontology Society, the society that runs like PDU3.
Yeah, that's right. So Nicholas Campione is the president of the Australasian Paleontologists at the moment, and Marissa Betts, my supervisor, is on that committee as well. So I guess you could say that the AAP, the Australasian Paleontologists, is kind of housed at UNE at the moment. We pass it around to different universities and different groups, which is really wonderful, and it's our turn to look after it. And we're hoping it'll be a really exciting time for Australian paleontology, particularly for our early career researchers who are still sort of up and coming.
Yeah, UNE is a very new school, and your paleo department is primarily staffed by sort of younger professors, as if my understanding is correct.
Yeah, we definitely have sort of a younger, early to mid-career researcher demographic here at UNE, and that makes for a really nice dynamic environment. And a lot of our student population as well are quite young. However, we do have the whole spectrum of different ages, genders, identities, so on and so forth. We're really proud of our diverse and supportive community at UNE.
And you yourself are a member of that diverse community, so it's good to hear it from somebody who's on the inside and has the knowledge.
Absolutely.
I did want to ask you a little bit more about yourself and your paleontological career to date. So, my understanding is that you've passed your confirmation. You're a PhD candidate. Congratulations.
Thank you.
So, you've come from paleontology from more of a geological background, whereas a lot of people might assume that paleontologists come from more of a biological background. Could you tell us a little bit about what that experience is like and how you feel your perspective might differ from somebody who came in from more of the organic living side of things?
Yeah, of course. That's a really good question because I think a big misconception that people have is that you can rock up to a university in Australia and say, I would like one bachelor in paleontology, please. And the degree doesn't actually exist. So we have to, as paleontologists, we sort of build our skill sets through different avenues. A really popular one is that biological science side you were talking about, with units around paleontology to get you that sort of fossil background. Or alternatively, you can take the geology side as well, which is what I did. And I think something really important that I want to emphasize is there is no right or wrong way to do it. I certainly felt that after I got my bachelor's degree in geology and I wanted to get into paleo research, I kind of at first felt a bit unsteady on my feet, and I felt like maybe I'd made the wrong choice because I looked at all these other students around me who had these really biology heavy backgrounds, and yeah, they seem to just know so much more about the animals themselves that we're studying. And I was really quite worried at first. But it's important to remember that as part of your research career anyway, you are constantly learning and developing and changing. And I sort of found that having that geology background really helped for the kinds of things that I'm interested in paleo. So I'm less interested in what the animals might have looked like or did or what their behavior was, but I'm rather more interested in things like paleo environment, telling time through geological history, and determining what sort of bigger global things we can answer with the fossil record. And for that, we need the rocks.
That's a really excellent point. Paleo environment is a topic that I feel goes a little bit under discussed in Australia because we are in kind of a golden age at the moment with new species being described both in the vert and invert world. And it's always exciting when you see, a friendly new little creature that shows up, but it's important that we have something called the paleo environmental context for these things. So for those of you playing along at home, the paleo environment is the environment these animals would have lived in however millions of years ago we find them. And that can actually be a very difficult puzzle to solve. My understanding is that the Cambrian presents a lot of unique difficulties, especially the early Cambrian. If you could speak a little bit more to that.
Oh, I'd love to, Alyssa. So the early Cambrian, which is what I mostly focus my research on, happened about 500 million years ago, or 500 million years, I like to say, just because that's got a bit of extra pizzazz to it. And studying paleoenvironment or making paleoenvironmental interpretations from the Cambrian fossil record are really challenging because life was really different back then. During the Cambrian, we saw most animal groups appear in the fossil record for the first time, some of them looking quite like what we might expect them to today, like very early brachiopods, and others looking completely wild and different. You might have heard about the Cambrian weird wonders before. And so when we're dealing with these animals that are incredibly different, in some cases not so different, in a world where life was really different because life was just working itself out, can be really challenging to work out things like paleoenvironment because we can't apply modern analogues as closely as we would for other times in geological history, such as when the dinosaurs were alive. Life, ecosystems, and environments sort of started to reflect more modern day things. But back in the Cambrian, it was nature's experiment, I like to think of it like, and we know that things like seawater chemistry and geochemistry were behaving really, really differently, and it actually might have been part of the special ingredient, you could think of it, to sort of spark this diversification of life that we see.
Yeah, I mean, I think that's something people don't really know much about. It's often been portrayed that the Cambrian is like this, whoa, it's so weird and different, we can't get any answers kind of situation. And I think that indirectly stems a little bit from the way that Stephen Gould kind of wrote about it. And I know that probably was not his intention, but people often struggle to conceptualize the Cambrian because it's hard to imagine a space, I think, where you've got like these very, yeah, like you said, these nice mollusks, these little clam-like fellows called brachiopods that are swimming along, in an ocean that's chemistry is very different. So if you could speak a little bit more to those sorts of different ocean chemistries and environmental factors that may have played a role in that early radiation, that would be awesome. Especially, I think there was something called the, gosh, I can't remember what Greg Cohn called it now, the Savannah hypothesis, but underwater or something like that. This idea that early reef builders creating this brand new 3D environment was a major driver in evolution because prior to this, we kind of just had our little gooey ediacaran creatures hanging out on the goo mat, and now they're in a 3D space.
Yeah, so I guess maybe a really good place to start is by talking about the sort of transition from pre-Cambrian time, so we call it the Ediacaran now, through to Cambrian. Now, it's really important to sort of note that a lot of people like to think of it as a black and white kind of concept. Like we had the Ediacaran and then the lights went off and then we had the Cambrian. And it's not really quite like that. It's very transitional. And that's pretty normal as you might think. It's a very parsimonious way to think about how nature might progress. But in the Ediacaran world, just before the Cambrian, we had a lot of organisms that we don't really know a lot about, but we also had microbial mats that coated the seafloor. And they were really important in some of the ways that we see Ediacaran organisms preserved today. If you go to the Ediacara site in South Australia as an example, at Nilpena, and through the boundary between Ediacaran to the Cambrian, we had something called the substrate revolution, which is a really cool way of saying that animals started burrowing. And as they burrowed, they broke up this microbial mat, and that loss of microbial mat allowed for these early reef-like forms to start proliferating. And I say reef-like because some of these early reef builders, such as archaeocyaths, are kind of like modern reefs, but they're also kind of not as well. And I know the biologists would come for me if I called them reefs. So reef-like is what we're going to go for. And essentially what these early reef builders did, archaeocyaths are a type of sponge, we think, that secreted a calcareous skeleton. And together with some friends, some microbes called Gervinella and Rhenelsis, it glued itself together to form framework reefs, quote unquote. And there's this idea that as that expansion evolved, that it was an ecosystem engineer and drove diversification of these animals. So if you have an environment that becomes more complex with time, the idea is that the animals in turn will become more complex as they can take advantage of these environments. So these little holes they could hide in, maybe it will help with foraging or predation, so on and so forth. And that really helps to sort of drive this early diversification that we see. And you mentioned before the seawater chemistry as well. I want to talk a little bit more about that. We're not 100% sure at the moment. This is one of the big questions that we're still kind of grappling with. But we know in the Cambrian that potentially there was more availability of things like calcium and phosphate in the water, which allowed animals to secrete biomineralized or hard shells. And that was a really critical step in animal evolution, actually. It doesn't sound all that exciting, but when animals worked out how to biomineralize, Well, life got cool, if you ask me. But it also meant that these animals could protect themselves, diversify. We start to see some of the really iconic animals from the fossil record, such as trilobites. And it was a really critical major step in animal diversification. Once animals worked out how to biomineralize, it was kind of all up from there. And to today, biomineralization is one of the fundamental toolkits of nature that we still see. You go to a beach and you pick up a shell, that's biomineralization. Nature worked that out 500 million years ago.
It's fascinating the stuff that hangs around and how set a lot of those characteristics kind of become. I mean, when we look at biomineralizers in that early ocean, we're seeing a lot of, like you said, really similar traits to animals that we see today. A lot of really definitive arthropod characteristics show up basically right at the start. My understanding is that your work, as somebody who's working at a lot of this biostratigraphy, has a lot to do with trying to match these beds that are occurring from this earliest Cambrian when we don't necessarily have species that are globally distributed to tell us where we are in time. Something called index fossils, where you just go out to an outcrop, and if you find a very specific type of fossil, you have a good idea of where you are in time. Now, my understanding is that the early Cambrian doesn't really have that, so you guys are using something called a multi-proxy approach to discover what might be going on there. Is that a good summary?
Yeah, that's a good intro to it. So with biostratigraphy, there is a really big challenge that we have in the Cambrian. So you might have seen how we find certain types of plant fossils in one country today, and we also find it in another country. So we know that those lined up once upon a time when the Earth's continents were in a different formation due to tectonics. It's not that simple in the Cambrian, unfortunately. For a lot of continents, we have some ideas, but we don't really know exactly where in the globe they were at the time, nor do we know what other continents they were attached to. So that's challenge number one. And that's something my supervisor, Dr. Marissa Betts, is working to solve at the moment, which is really exciting. But challenge number two is that different faunas, different groups of animals are local to different areas. And we see that today on Earth. And so sometimes what we can do instead is build more local schemes. So for example, we have a scheme for Australia for using different organisms and animals from the Cambrian to work out a relative age. And what we mean by relative is that we can work out that these rocks are younger than these rocks or older. And then from there, if we have a volcanic rock, they have special minerals in them called zircons that we can use to accurately date, so we get a number. We love that. And then we can sort of trace these beds and work out where all the different layers sit and go, so these beds they must be a little bit older than that volcanic bed over there. And so that gives us a relative handle on our age of deposition of different kinds of rocks. So that's sort of the classic way of doing it. But as Alyssa said, we use something called the multi-proxy approach. So as well as using the fossils straightforward to make a relative age, we also use the volcanic beds, and with our our number ages, they're not quite accurate. We've got wiggle room of a few million years either side, but in geological terms, that's quite good. And then we also use things like chemostratigraphy, so the amounts of carbon and oxygen left behind in these rocks. And they track these lovely little curves, and we can match up the different curves to different periods of time. And these we see, it is an emerging science still. We're still learning a lot about this, but we see these emerging patterns, and they're not just wiggles on a curve. They fit within a certain numerical range, and we know that's that curve there, and that gives us another relative age as well. So if you've got a relative age from your fossils, and you can get this data as well from your isotopes and go, that's also agreeing, happy days, because what we want to do is get as many different forms of evidence to back us up that this is the right age. Why have one when you can have multiple? And if they're all saying the same thing, then that tells us we're probably on the money.
That's really interesting. I know you were doing a little bit of stuff with the Second Plain Creek member and what we call the Red Horizon for your honors project. And I know that because I was in the field with you. Do you want to talk a little bit about how that fit into this multi-proxy approach?
Yeah, absolutely. So what we did is we had a rock unit in the Flinders Ranges. That's where I do a lot of my research. And we knew very little about it because it only, we say crops out, means it only appears at the surface in one location, which is rather difficult to get to. So as Alyssa might recall, it involved some fairly intense climbing up boulders and that kind of thing to get there. And so we were kind of working with a clean slate with the Second Plain Creek member. And so we utilized the multi-proxy approach to determine a few different things about it. So we wanted to know what diversity of animals were living there. We wanted to know its depositional environment and also roughly how old it was. And so to determine what animals were there, these rocks are carbonates or limestone. And inside them, the little fossils they have, we call them small shelly fossils. And as the name suggests, they're pretty small, typically less than 2 millimeters, much less than 2 millimeters, I should say. And they're made of, they would have originally been organophosphatic or made of calcium carbonate, but have been replaced by phosphate. And that's how we have them preserved in the fossil record. Now, a really cool thing, if you have a limestone with phosphatic fossils in it, is they're really easy to get out. So what we do is something called acetic acid leaching. So we chuck our limestone in basically very strong vinegar that dissolves away the carbonate and leaves behind a bit of residue and these little phosphatic fossils that we can pick out under microscope and identify who we have. And we had exactly who we would expect to have in the Second Plain Creek member. So that was really good. And from those fossils, we were able to work out a relative age because we'd already made a scheme for South Australia in the Cambrian of what animals where meant what age. And then we were able to back that up with the chemostratigraphy. So I sent away lots of tiny little powders from the different rocks, and they were measured for how much carbon and oxygen they had left in them. And it gave me a wonderful curve that told me yet again, yes, this was the right age, about 517 million years old, if you're curious on an exact number. And then to determine the depositional environment, I did a lot of what's called carbonate microfacies work. So looking very closely at these limestone rocks and the different features that they have to tease out what environment it was preserving at the time. Now, we like to say that carbonates are born, not made. And so unlike other kinds of rocks that might form through the gluing together of other smaller rocks or sand compacted over time, carbonates have a biological component in the way that modern reefs do. And so they're really, really good storytellers if you know what to look for. And what the carbonate environment showed us is that it was continuous, that these rocks were capturing what happened, which is important for relative age, because if you've got a big chunk of time missing or something else has gone a bit amiss, you've got some faulting or folding, you've got to take your results with a pinch of salt. And they showed us a really beautiful transition from the younger rocks, which were capturing a shallow reefy environment, to the next rocks in succession, so younger yet again, that were showing a very deep, sort of peaceful marine environment. And so we're going from shallow, happy reef environment to sort of deeper water marine. And we didn't have any idea what was going on in between them. And now we know that it was a ramp, which makes a lot of sense. And it became deeper through time.
I think you've explained it really, really well. And that's fascinating because it's one of the few times we get a complete snapshot like that. Like Steph and I can both rant for days about how cool the Flinders deposits are. But essentially, when we're talking about rocks that are more than almost 500 million years old like this, the chances that that rock hasn't undergone some kind of folding, twisting, pressure get slimmer and slimmer. And in the Flinders, we have this gorgeous outcrop where if you think about stratigraphic layers as being kind of like a deck of cards, they've kind of splayed out due to some pressures as plates changed position. And it's a really complete succession as we're moving from that Ediacaran period into the Cambrian. It's one of the most complete successions, in my understanding, that we have in all of Gondwana, if not the world. It's really unique.
Yeah, you're absolutely right, Alyssa. And that's one of the really important aspects of the UNESCO World Heritage nomination for the Flinders Ranges, which I've been involved with. And that's a really exciting avenue to protect these rocks and to, I guess, really state their significance to the world.
Yeah, I guess tell us a little bit more about what you've been doing lately. What is your PhD focused on? Is it continuing kind of the same trend? Are you still looking at the Flinders, or are you looking more at different global deposits?
So I'm still working mostly within Australia, although I have included a few global deposits. But what I'm looking at more broadly for my PhD is how these different fossils are preserved. Now, in the Cambrian, lots of weird things are happening, as we sort of touched on before, and that extends as well to how fossils are preserved. So those small shelly fossils I talked about, those little critters with shells, they get preserved primarily by phosphate. We don't really know why there was so much phosphate hanging around to preserve them, but we have it. And that's really normal for these shelly fossils to be preserved because the fossil record is biased towards organisms with hard parts. That is, it's much easier to preserve a shell or a bone than it is anything soft because basically it's just a mineral replacement, or we can get molds and stuff like that. So it's very easy and straightforward. But in the Cambrian, if we were to rely on those small shelly fossils alone, we wouldn't see the whole picture. So in marine ecosystems, and this is true to this day, most animal diversity is represented by animals that are entirely soft-bodied. Now, unfortunately, that's a bit tough if you're studying diversification in the early Cambrian, if most of your animals are soft-bodied and the fossil record doesn't like preserving soft things. We are in luck in the Cambrian. We have something called Burgess Shale type deposits, or otherwise called Lagerstätten, and basically they are exceptional preservation sites that preserve soft-bodied organisms. They're really iconic, and they're the source of what we call the Cambrian weird wonders, and they were really, really important at capturing a huge array of diversity that we wouldn't have seen otherwise. If we are getting different types of fossils or different types of organisms preserved in different ways, is there a way we can combine all of these views to get a better understanding of diversity in the early Cambrian? If we just look at one and one only, we kind of have these little horse blinders on, and we're not seeing the full picture because we do get some organisms that fall under the small shelly fossil category preserved as Burgess shales, but not always, and there's only a tiny bit of overlap. And what we need to do as paleontologists, if we want to say anything about early animal biodiversification or evolution, is to be able to look at these as a big picture. Now, a particular challenge that I'm working on in this space is Australia's answer to the Burgess Shale, which is the Emu Bay Shale. The Emu Bay Shale preserves all sorts of organisms, from things that biomineralize through to entirely soft-bodied organisms. So it's a Lagerstätten, that's great. However, it doesn't preserve fossils in the same way that the Burgess Shale and others like it do. So the Burgess Shale preserves fossils as thin carbonaceous films. So the fossil that would have originally been some sort of wonderful squishy animal, picture anything you like, and it ends up getting squished and reduced to a carbon film that is like as 2D as you can get it. Whereas in the Emu Bay Shale, we don't see these carbon films, and more importantly, or perhaps more coolly, we see a little bit of 3D relief associated with these animals. So this is a completely novel way of the fossil record preserving things that we just don't really have a handle on at the moment. And that's a question that I'm working on with some wonderful colleagues to answer why the fossils at the Emu Bay Shale were preserved in the way that they are, how that happened. And I think it's just wonderful to be able to say that Australia's a bit different. We've got our own way of doing it, and this is how.
Yeah, I think people don't realize that Australia's had a very unique fossil record for most of its existence, and it has existed for a very long time. My understanding is also that the Emu Bay deposit is very geologically different as a setting from a lot of these other Lagerstätte, right? It's got like a hypoxic zone as part of its basin stratigraphy, if I understand it correctly.
Yeah, so most Burgess Shale type deposits, there's about 40 of them globally, and they sort of have a few main criteria that they meet. That is anoxia, so a lack of oxygen. That's really important because we don't want our animals to decay really fast. Otherwise, they'd just rot away and we wouldn't have them in the fossil record. And they also exist in environments that are very calm and relaxed. They're a fair way away from the shore, very fine mudstones. They're very chill environments. And the Emu Bay Shale is anything but. While there is some lack of oxygen at the sediment interface, which is important, the upper waters were most likely oxic. They still had lots of oxygen, and we had the kinds of animals that like Anomalocaris, or other radiodonts that liked to swim around hanging out there. But it was likely the deposit formed in what we call a microbasin, or a very small little bathtub, you could think, small relatively speaking, where we had heaps of sedimentary material dumped off of a delta. And that's super, super unusual for a Lagerstätten style deposit, because these kinds of episodic events that were dumping heaps of sediment are really, really unusual to what we normally know, which is that sort of quiet, peaceful, gentle environment. And that unique environment also reflects the kinds of animals that we recover from the Emu Bay Shale. So the predominant taxa that we find there is a type of trilobite. It's called a Stangia bilobata. It's a very cute little guy. And you can get hundreds of Astangias on these very small areas of rock. There's just so many of them. I call them cockroaches. You cannot get rid of them. Now, these little guys, we know were living in this sort of microbasin area that probably didn't have a lot of oxygen, because we find their molts. Trilobites molted their hard exoskeletons as they grew bigger in their life. And because we find the molts and also the dead animal as well, all complete, we know that they were living in that space. And it makes sense that they probably could handle a little bit trickier of an environment. The cockroach analogy works even better now. And then we find fewer of what we call benthic animals, or those animals like Anomalocaris and other cute friends like Isoxes and Tuzoia that liked to swim around in oxygenated waters. And what probably happened to them is they died somewhere else and were dumped in these big episodic events, these huge amounts of sediments being dropped off the delta fan.
I think it's really interesting because every one of these different deposits that you're talking about, all of the 40 across the globe, because we are looking at local populations a lot of the time, the faunal assemblages that you get are often so unique. And it's incredible that we have this unique deposit, this unique environment, and these unique animals. I think, gosh, what was it? 2022, 2023, they described a new radiodont, Echidnacaris from Emu Bay Shale.
So Echidnacaris used to actually be called Anomalocaris sp, or SP, which means a species of Anomalocaris. And it looks really similar to other Anomalocarises that we have in the fossil record. But in 23, some awesome scientists worked out that it's its own unique type of radiodont and named it Echidnacaris. A lot of the new and unique taxa that we have out of the Emu Bay Shale have awesome names like Echidnacaris and Kangacaris, because we just love calling them after Australian animals. Most fitting.
It beats naming them after some dead person we've never met.
It sure does.
So I have two places I want to go with this. First, I guess one of the important things to think about as well that I imagine goes into your work a lot is this idea not only of taphonomic bias, so how the dead thing gets preserved, but then how we process the rocks in order to get the fossils out. Because when we're extracting phosphatic shelly fossils in our big, very smelly vats of vinegar, I've been in that room, it smells like pickles. It's great. In order to get those fossils out, we do dissolve away other fossils that are preserved in different types of materials. So there's a choice that we end up making when we process the fossils a lot of the time between what assemblages we're getting out at a given point, if that makes sense. So is that something that you end up having to think a lot about?
Often in our carbonate rocks, we can have things like those early reef-like builders, Archaeocyaths, preserved in them along with our shelly fossils. But the Archaeocyaths are preserved as calcium carbonate. So if we chuck that in that vinegar bath, we lose them. And that's a bigger challenge about Archaeocyaths that I'm also working on at the moment. Very ambitious PhD project. But most of the time we find that this phosphatic preservation dominates how these fossils are preserved. And so it's not really, you might lose one or two things, but for the most part, they will come out all right. Alternative pathways for preserving those fossils include bisilica or glauconite, much rarer, but it does happen, and those two will remain untouched by the acetic acid, so we're safe in that avenue. Whereas there are different processes for acid leaching for different kinds of rocks and different kinds of fossils, but it really depends how, you need to put your chemist's hat on for a second. It depends what kind of rock you have, and what the fossil is made of depends what kind of chemical you might like to use to extract it. So if we have rocks that are, we call them siliciclastics, but that's a big fancy word for made of dirt. as I like to put it, sand or silt or mud, or I've got to say that, otherwise the geologists will come for me. These rocks we dissolve in completely different methods as opposed to that acidic acid because the chemistry just won't react.
I wanted to ask you a little bit about how you got into paleo to begin with and some of the leadership roles that you've taken on as a more senior student to a lot of the people, both the undergraduate students at UNE and the incoming PhDs. So I know that you've talked a little bit about your journey into geology, but I guess what is it that motivated you to come into paleontology and what keeps you here?
Oh, that's a great question. Now, I guess the answer is really quite similar to what a lot of people's is, and that's when I was a little kid, I loved dinosaurs and I never grew out of it. To be very particular, it's a very interesting story, but I was in 3rd grade and we were learning about dinosaurs in class. And for whatever reason, I guess back then, which was a couple decades ago now, our idea of what dinosaurs were was quite different to what it is today. And we were still very much in that sort of big, mean, scary dinosaur era. And so to a little kid, that was terrifying. I hadn't quite grasped the concept that they were dead for a very long time, but I was terrified of dinosaurs. And so, being a very imaginative and, I guess, proactive young person, I decided I was going to make up an imaginary friend that was a sauropod that was my friend. And so I learned to love dinosaurs through this imaginary friend situation I had made up, so I wasn't afraid in class anymore. And I just didn't let it go. And it went nowhere. It was still there. I started volunteering in natural history as a teenager because guess what? I still loved dinosaurs. I was like, I'm going to get a job in this. And even though a lot of people sort of said, there are no jobs in this, what are you doing? I stuck true to it, stuck true to my dream, and picked a degree through distance education with UNE that I felt would help me get towards my goal of paleontology, but also give me a really solid background in a science that I'm interested in that could help me out if the paleo thing sort of struggles to work out. And so I always knew I was interested in the what and the why kind of thing. So geology made a lot of sense to me because how the earth is made up kind of explains everything, really. So I thought that made a lot of sense for me to study that. And through studying geology, I fell in love with it a lot more than I thought I was already in love with it. And it gave me, I guess, a sense of idea that I can do lots of different things with myself now. And I'm also very comfortable with the idea that, maybe one day I end up working in geology instead. And that's a really awesome thing to have up your sleeve as well.
So what would be like a good piece of advice that you would have given to either your younger self or to people who are interested in paleo and are maybe in similar positions to you where they're very young and they're just not sure what might be right for them?
Yeah, look, it's not an easy world to navigate by any means. I think particularly as very young adults, we're trying to grow and develop as researchers, but also we're growing and developing as individuals and people. Whiplash is the word that comes to mind. Imagine finding yourself while doing a PhD. It's hard. But I think the advice I would give to people is really to go with the flow. Take the opportunities that you like as they arise, and it's important that these are things that you're actually invested in. If you're offered an opportunity and you're like, that doesn't really crank my tractor, let it go for the next person. And that's not a bad thing. In fact, that's a wonderful thing for the next person who gets offered it and gets to take it up. And yeah, so overall, I think I would really say to be okay with the idea of change. My life as a paleontologist now looks nothing like I thought it would. I don't study the animals I thought I would. I don't study the time period I thought I would. Everything is just about as different as it could be. And I wouldn't change it for the world. I know this is exactly what I'm meant to be studying and what I'm meant to be doing. And I would be so sad if I didn't have the experiences that I have had in my life. But I wouldn't have had those if I stayed really stuck in my lane and didn't take, I guess, a leap of faith from time to time. Obviously, it's important to do that in a safe way, but it's really important, I think, to sort of allow yourself to branch out and explore different things. And it's okay if your life isn't what you thought it was going to be originally.
I think those are just good words to live by in general. That's really comforting.
I'm glad.
I also wanted to ask you a little bit about how it is to be a young, very driven woman who's taken a lot of leadership roles in STEM. You've led a lot of classes as a teaching assistant, but you also play an active role in a couple of different geological and paleontological societies. Have you had a lot of challenges going into this field as a woman or as somebody who's in the queer identity spectrum? And do you feel comfortable to talk about them?
Yeah, so look, everybody, I think it's really important to say that everybody's experience in the space is really different. And just because my experiences are one thing doesn't change what somebody else's experiences are or what might happen to them in the future. And really, this space is still developing, right? Like, the women have had the right to be in the workforce for a very, very long time now, which is wonderful. But for some industries, we're still kind of catching up with what that might actually look like. And, unfortunately, there have been experiences for me where, particularly as a very young woman as well, I'm often overlooked or babied to a degree and had some really nasty, awful comments made to me. But then on the flip side of that, there is also a really wonderful, supportive community who really want to drive and see this diversity, be it gender or queer identities and so on and so forth, within paleontology, because remember, at the end of the day, paleo is just a reflection of the real world, and we see all sorts of people in the real world. And I think that's like a really important note to make, is that this science is for everybody, and definitely it is changing towards that in the modern day, which is really wonderful. We're starting to see a lot more diversity, as I'm sure Alyssa can attest to. But beyond those sorts of challenges, I think something that I take a lot of heart in is every time I experience a challenge like that, might be related to my gender or how I present myself or my age, I think that I am doing the groundwork to make it easier for the next generation. And that's something really, really important to fall back on, I think, that it keeps me going in the darkest times, because I know that every step that I take, every time I speak up, every time I help somebody else is going to make it easier for the next person who comes through. And I think that's a really important thing to do and a really important way to think about it as well, and makes it much easier for me. Now, with, I guess, my teaching avenues as well, it's such an interesting experience teaching undergraduates, and a lot of words come to mind. I think sometimes it's terrifying, sometimes it's exciting, and other times it's challenging, but also really rewarding. And it's because I think it tests your sense of self and the sense of confidence you have in yourself. And I think a lot of people in general sort of suffer from, in things like imposter syndrome, lack of self-confidence. We're very quick, particularly as Aussies, to sort of cut ourselves down a bit. And so you get to this environment where you're put in front of students and teach them, show them the ropes, and you go, oh dear. And then you do it and you go, hang on, I actually know stuff. And you get to the end of that experience and you go, wow, like you've really shown to yourself that all these things you've learned have stuck with you and you can pass them on. Teaching is the best way to learn stuff and to consolidate your own learning, which I really, really enjoy. And for me, it's just a challenge in the sense that I want to be better every time. And it's so wonderful, I guess, to look back at earlier versions of myself and see how much I've improved and also how much more confident I've become.
It's a really good way of looking at it. And I agree. It's certainly a challenge to your own knowledge and your own confidence in it, because that is such a different skill set, teaching, compared to what we do in the field or writing a paper. I just wanted to close out with two questions. One will be a little more serious and one will just be for fun. So the serious one first, what do you think has made the biggest difference in your trajectory in paleo so far?
Oh, that's a really big question, and it's a really important one, I think. And the two things that come to mind are opportunities and people. So I sort of talked about it a little bit before about taking opportunities and putting yourself out there a bit, which is terrifying. I'm not going to sugarcoat that. But taking up these different opportunities is so important to learn what you like, learn what you don't like, which is just as important as knowing what you like. It's also really important to sort of get your name out there. People aren't going to ask you to help collaborate on their research if they don't know you exist. So the more you get yourself out there and take these opportunities, the more they compound. And that's what's really helped build me as an early researcher. And then the other side for that is people, surrounding yourself with wonderful, supportive people who can help you get to where you want to be, to inspire you and motivate you, particularly if you find yourself in a minority demographic, to surround yourself with as many of that demographic as you can is really helpful. So finding a community of women has been really, really helpful for me to sort of bounce these shared experiences off. And like breeds like, we always like to think. So the more women there are in a space, the more women that will come. And that's really, really wonderful and really important, I guess, in how I've been guided through my early career.
I think it speaks a lot to the kind of environment that the institution fosters as well. Like UNE seems very open to having this queer, diverse, female-oriented group of paleontological students and researchers. And I would say generally Australia seems like it is experiencing kind of this boom in paleo, where a lot more people like you and me are capable of making a difference and getting our voices out there. But the final question I have for you is, what is the best fossil? Alternatively, what is the worst fossil?
Well, I'm going to answer both. And I think the worst fossil is some kind of forgery, right?
Yes.
Like if I've made up some silly thing and I'm like, I have solved the Cambrian explosion with this weird fossil I glued together, that would be bad. Other than that, there are no worst fossils. All fossils are good fossils as long as they're real fossils. I think the best fossil, this is probably not the answer you're hoping for. You're hoping I'm going to say Spinosaurus or something, but I'm not. I think the best kind of fossil has good stratigraphic context. And what that means is we have a good lot of different rocks around it. And that really tells those stories that I'm interested in, how these fossils were preserved, what the paleo environment was like. And without having a really good context of those rocks around, we wouldn't be able to answer those questions. So that's my opinion on what the best fossil is.
That's so valid. The amount of time that you have spent getting rock that is in situ, so stuff that is still in its geologic context, out of precarious walls, I would probably feel the same way. That's so valid. Well, thank you so much for telling us all about your work today. Where can listeners of this podcast find you on social media and also in the wild, I suppose, if you're to be found like a Pokemon?
If you'd like to find me in the wild like a Pokemon, you can find me at the University of New England. I work in the Earth Sciences building. If you poke around, you will find me. I'm almost always there. You can also reach me on my Instagram. My handle is biostratigraphy, which is a bit of a mouthful, BIOSTEPHIGRAPHY. That's my public science communication account, and you can find me there and also contact me there as well.
Awesome. Thank you so much for your time today, and we look forward to seeing what happens next in your career.
Thanks so much, Alyssa. Thanks for having me.
Alyssa, that was such a fun chat you had with Steph. I really enjoyed working on it and listening to it, and I hope for you it was a good first intro to the podcast. What was your favourite part of that combo?
I had so much fun talking to Steph. I think she explains a lot of really difficult concepts super clearly. I'm very envious of how well she communicated her science. And as nervous as I was, it's always easier when you're talking to a friend. I really enjoyed hearing her field story from Mongolia because it's a part of Steph's life that I don't know as much about. And it's always been so cool. She always finds such good fun out in the field.
Awesome. I want to mention as well that in part of this new refresh that we have going on, we have a brand new logo which has been created by Zev Landis. We're going to have Zev on to talk about his art. It represents sort of two sides, me and you, I guess, because there's a trilobite and there's an Australovenator. And the thing that we realized is that both the trilobite and the Australovenator need names.
Absolutely. So maybe you guys could help us out by coming up with some fun new names for our mascots.
Yeah, I reckon those who submit the best names, we'll list them on the website and we'll send them some stickers. Sound good?
That sounds awesome. And you're very lucky to get a piece of Zev Landis art on a sticker like that. So very exciting.
We'll talk to Zev a bit more detail about his art in a future episode. But for now, jump on to any of our socials tell us what you think of Zev's art and our new logo, and also suggest names for our trilobite and australovenator. As soon as we have two that we'll like, the competition's closed. We're just looking for some great names. We want to hear from listeners out there. And, also share thoughts on anything else we've discussed or any episode ideas or other cool paleo stories. You can find us on most social platforms. Final segment I wanted to bring into today's chat, Alyssa, is going to be a fun one, I hope. Fossil, fact, or fiction. Here's me trying to trip up the paleontologist, but let's see how we go. So you need to tell me if this first fact is a fact or is it fiction.
Okay.
There was once a prehistoric penguin called Kumimanu that stood about 1.75 centimeters tall, which is taller than many humans. I think is it maybe taller than you or pretty close? So picture a penguin, right, that's going to look you directly in the eye and could even bench press you because this is a big penguin. It lived around 55 million years ago, so only 10 million years after the KPG extinction. It was found in New Zealand, and I think it completely shatters the cute, waddling penguin stereotypes. Is this fact or fiction?
If I get this wrong, Astrid in my lab is going to be so disappointed with me. I'm going to say fact because I've seen a very unhinged paleo art drawing of a man hugging one of these creatures, and I want that to be real.
Humans weren't around then, but of course, but it's fact, right? It's amazing to have a penguin that big, particularly that early after the KPG. Kumimanu is an incredible penguin, absolutely huge. It would be amazing to see one of these things waddling around on the ice or on the coast where the penguins lived. Imagine if you were there watching the little penguins down in Tasmania or Victoria, and one of these beasts as tall as a human just came wandering over the over the sand or the rocks.
I would just run.
Okay, second one. A groundbreaking new fossil discovery reveals that certain dinosaur species had specialized skin cells that could potentially change color and pattern instantaneously, similar to a modern-day cuttlefish or lizard. This could have provided unprecedented survival advantages in diverse prehistoric environments. What do you think about this one? Because we know there are findings out there that can show us potentially what color dinosaur feathers were or even skin patterns based on melanosomes. That is a fact. Is it a fact that there has been a discovery that shows some specialized skin cells that could change color?
As much as I would love a chameleon iguanodon, I'm going to say fiction.
Yes, it's fictional. It was made up. I love that you were almost convinced by this.
I want it to be real. I want the Stegosaurus to have little flashes. That would have been so cool.
Isn't that the sort of one of the leading theories on what Stegosaurus plates were for, right? Is that they had some blood vessels that could flash and change color, but maybe not the same way as we see with an iguanodon or with a chameleon or something. So, well, what a shame. We do get the giant penguin. We don't get color-changing dinosaurs as far as we know. Alyssa, this has been such a fun conversation. I'm so glad to have you on the podcast. We are looking to do a lot more renovation to the format as we go, a lot more fun segments and things like that. And I absolutely cannot wait. So this is a great time. If you have listened to Fossils in Fiction, now is the time that you really should pick it up because there's now someone here who knows what they're doing. And we're going to have, I think, a really good time. We're planning to release episodes fortnightly. We're getting a couple of episodes in pre-Christmas, but from then on, it'll be fortnightly throughout 2025. So please join us, follow us on our socials, rate and review, all those good things. This is Fossils and Fiction, where culture and science meet together in paleontology. Alyssa, thank you so much. Talk soon.
Thank you so much. Thanks for joining us for this episode of Fossils and Fiction. If you enjoyed the show, be sure to rate, review, and follow us on your favorite podcast platform.
And don't forget to connect with us on social media. Share your fossil-inspired stories, art, or questions. We'd love to feature you in an upcoming episode. Until next time, keep exploring the culture and science of paleontology.